lecture series on real analysis. In this lecture, we are going to see a Weierstrass theorem. This Weierstrass theorem is a part of compact sets, and let us see what is given in the theorem. Okay, here every infinite bounded subset of Rk has a limit point in Rk. Okay, how are we going to prove it? Right. So let us start the proof formally. Okay, here let us take E to be the bounded infinite subset of Rk, right? So here we are going to make use of the boundedness of this set. Since E is bounded where? It is bounded in Rk. Since E is bounded in Rk, there exists a K cell I such that this E is contained in I. Right? We know that K cells are compact. Right? So directly we may write that I is compact here, because we know that every K cell is compact, and we also know that an infinite subset of a compact set has a limit point in that compact set. Using that theorem, we can say that E has a limit point in I. So when it is in I, we know that this is a subset of Rk, right? So it has a limit point in Rk. This completes the proof of this theorem. If we have to prove it formally, you can make use of the ideas like where we prove K cell is compact, and every infinite subset of a compact set has a limit point in the compact set. Using those two theorems, we can formally prove the Weierstrass theorem. Right? Now let us see some examples of compact and non-compact sets. Right? Hope in the Heine-Borel theorem, the idea of the compact sets in Euclidean space has reached you people. That is okay. Let me take this to be my set E1, okay, which is a subset of R. I am talking, and E2 to be the open trivial of R. Here I have not specified about the metric that I am talking. Okay. So if the metric is not spoken here, we will have to assume that standard Euclidean metric is defined on it. Okay, and using Heine-Borel theorem, okay, we can prove this is compact. How? The set E1 is closed one, okay, and bounded to. So this implies E1 is compact, right? Next, E2 is bounded. This is very well bounded, but this is not closed with respect to the standard Euclidean metric on R. With that, we may come to the conclusion that it is not compact. But if we have to try by the definition of a compact set tells you what? Every open cover has a finite subcover. Okay. First of all, let us try to identify some open cover of the 0, 1. Okay. Open cover of E2. Some of you may think in a way that let me take my G1 to be 0, 1 itself. If this is the case, what am I having? I have my E2 is contained in G1 itself. Okay. This is the only set. Let me put that in the collection, and this is the case. So it has a finite subcover, right? Then why can't I say this is compact? This may be the case. Or sometimes, let me define Gn to be 0, n, where n runs in n. Okay. Even here, your E2 is contained in union of this Gn's, and you can identify some finite collection here such that your E2 is contained in the union of the your E2 is contained in the union of the finite thing. That is, if you just take only the G1 G1 union G2, okay, it is going to be contained in it. In this way, we may think that is not wrong, but the definition very well tells you that every open cover has a finite subcover. So here these are some covers which have finite subcover. There may be some cover which do not admit any finite subcover. We will have to try and identify that thing to say this is not compact. Okay, let us try to explore that. Okay, let me define my Gn to be 0 comma wait 1 upon n comma 1. Okay, here n runs in n. Here if you make the union of all such Gn, what you will get? You will get 0 comma 1. Okay, so here what you have is that your E2 is contained in your union Gn, right? But does it admit any finite subcover such that your E2 is contained in this? No, right? So if you take the entire, here it is going to be a countable union. If you take the entire countable union only, this is happening. But for finite subcover, it is not going to happen. Here, okay, just a minute. Here, the collection Gn do not admit any finite subcover. Subcover of what? For E2 it is not admitting any finite subcover, right? Hence E2 is not compact. Okay, and if you start identifying any closed and bounded set in any metric space with any metric, those things will be compact or not? We cannot come to the conclusion. Yes, in Euclidean space, under standard Euclidean metric only, closed and bounded implies compact and compact implies closed and bounded. Now let us summarize the results that we have seen on compact sets, which will be useful while doing problems, right? In general, what are the cases we have? If a set is compact, then the set is closed as well, right? And if we take some closed subset of a compact set, that is also compact, right? If you take the intersection of a closed sets with a compact set, that is going to be compact. These are true in general, which means this is applicable for any metric space. And in particular, that is on Euclidean space, what are all the results that we have seen? These two cases will be compact, right? If a set is closed and bounded, then it is compact. If a set is compact, then it is closed and bounded. Here, in all these results, you may see that this one implies this. Only in this we have the both the things. Here you may see that compact always implies closed. Okay, that is true from this itself. But compactness also implies boundedness only in a Euclidean metric space. Okay, it is not true in general. So in the upcoming lectures we will work out few more problems on compact sets. If you have any queries in this lecture, you may post it in the comment section. That will be clarified within 24 hours of time. Thank you for watching.